This video is an introduction to mass spectrometry, determination of the molecular weight of an unknown compound. It's brought to you by the riddle, what can you throw but not catch? Okay, let's revisit the determination of a structure of an unknown compound using an IR spectrum. Normally when we're given an IR spectrum, we can make certain assessments about its structural characteristics. And in previous problems, we had determined likely Lewis structures, or the structure of the molecule, given an IR spectrum. But that always gave us additional information. For example, suppose I gave you this IR spectrum, and I said, draw a Lewis structure of the compound that is represented by this spectrum. You can make certain assessments right off the bat. For example, you might look at this and think, well, based on the peaks at 1400 and 2900, it's a saturated hydrocarbon. I don't see any alcohol. I don't see any carbonyl. I see a peak here, and maybe that peak corresponds to an ether peak, but you wouldn't necessarily be absolutely sure. Maybe you could identify this as a saturated ether, maybe not. At the end of the day, drawing an exact Lewis structure would be impossible. How many possible isomers could you draw that would represent this kind of infrared spectrum? The correct answer at that point is an infinite number. I don't think that we could narrow down how big or how small it is. We would need additional information. At an absolute minimum, if I told you the molecular weight of the compound is 88 AMUs, well, then perhaps you could start narrowing down a few possibilities for the structure of the molecule. If I knew it was 88, then I could start making certain assumptions about the molecule. Well, let's assume that it's an ether based on this peak at 1200 reciprocal centimeters. Let's even assume that there's only one oxygen in the molecule. Then we could start with 88 AMUs, and I know 16 of them are being used up by the oxygen. That means that 72 AMUs are being used up for the rest of the elements inside that molecule. If it is just carbons and hydrogens, well, then we have a limited number of things that are going to add up to 72. 72 would give me 6 carbons and 1 oxygen, but, well, that's not going to function because we can't draw a Lewis structure with any hydrogens. So maybe we could narrow it down to C5H12O. That's a possibility, at least. And based on that, we could probably draw a few different isomers, assuming all of our guesses are good, of what might be possible. But the truth is, even given just this information, we would have to make several guesses and assumptions about the IR in order to get to a few different possible isomers. That's why molecular weight and empirical formula is really essential for structural identification given IR spectra. If we look at taking that same sample molecule and then putting it in a mass spectrometer, then we might have the IR and the mass spectrum. The purpose of the mass spectrum is first and foremost to determine the molecular weight. The empirical formula, that would be a bonus. If we look at the mass spectrum, the first thing we need to remember is that the mass spectrum will contain a number of different peaks in the spectrum, even though there's only one molecule. Those peaks are coming from the intact molecule, hopefully, and many of the fragments formed by the ionization process. If we look at this, we can see that we have a peak at 88, 59, 43, 41, 39, 31, 29, and so on. The first thing we have to do, figure out which peak is the intact molecule or the molecular ion. Identification of the molecular ion is usually pretty simple at a first blush. If we remember that the intact molecule has to be the one that weighs the most. It is not necessarily the most intense. 59, for example, is bigger peak than 88, but only in intensity, only in the abundance within the source of the mass spectrometer. The one that weighs the most is the one that hasn't fragmented. So we make the initial assessment that the molecular weight of this compound is 88, based on the fact that it is the one that weighs the most within the mass spectrum. The problem is, we don't know if we're necessarily looking at the intact molecule, or if it's all just fragments, and that could be very confusing information. So the other thing we have to determine is, how do you know that this is actually the intact molecule and that these are fragments? Let's justify that assumption. That comes about by looking at this spectrum and maybe observing something already. Notice that the molecular weight, the intact molecule, is 88. The fragments, 45, 43, 41, 39, 31, 29, 27. The predominant ones are all odd. The intact molecule is really the only even number in the spectrum. The predominant of the fragments are odd. This is not by accident. If we think about organic molecules, if we start with like methane or ethane, or even carbon tetrachloride, if we want to talk about that. If we add this up, CH4 has a molecular weight of 16. Ethane, just as a random example, has a molecular weight of 30. Carbon tetrachloride has a molecular weight of 154. Notice they are all even. This comes about because of the nature of atoms on the periodic table. If we look at the fragments of these things, a fragment, if we just broke that molecule at any of those bonds, they'd all be the same. We would form CH3 and an H. The fragment would weigh 15. If we broke this molecule, we could break off a hydrogen that fragment would weigh 29, or we could break it right there, and if we broke it in the middle, the fragment would weigh 15. If we broke this molecule, if we just popped one of those chlorines off, the mass of that particular fragment would also be an odd mass. The reason this comes about is because all elements on the periodic table fall into a peculiar category of having an even mass and an even number of valences open for bonding, or they have an odd mass and an odd number of valences open for bonding. For example, carbon weighs 12. It has 4 open valences. Oxygen, 16, has 2 open valences. Hydrogen weighs 1. It has 1 open valence. Chlorine, most common isotope 35, has 1 open valence. No matter how you add those up, an odd number with an odd number of valences means that you're going to have an even number of odd things. Hey, trust me, if you have this situation, you always end up with an even molecular weight and odd fragments. Unfortunately, there is one exception, and that is nitrogen. And the nitrogen rule comes about because nitrogen, weighing 14, has 3 open valences. Even weight, odd valence. So we have NH3, mass 17. If it fragments, it has even molecular weight fragments. So how does this help us? Well, initially it helps us a lot. If a compound has an odd molecular weight, that must mean we already know that it must have an odd number of nitrogens in the empirical formula. An odd molecular weight means nitrogen is present. But how do we know then? If we look at a mass spectrum. Well, if you look at a mass spectrum and you see what you believe is an even molecular weight, and you look, and the predominance of fragments are all odd, that suggests that this is the intact molecular weight. If, on the other hand, I had a mass spectrum that did not contain the molecular ion, it was fragile, it didn't show up, your mass spectrometer didn't collect it, and I immediately assumed by looking at this spectrum that the molecular weight was 59, and I thought, hey, it's nitrogen containing. But then I looked, and I saw all the fragments were odd. I would start to suspect that this is in fact not the molecular ion, not the intact molecule, but it itself is a fragment, since it is odd and the fragments are odd. If it's a nitrogen compound, the molecular weight will be odd, but the fragments will be predominantly even. So, by the way, a party. Assessing the mass spectrum for determining the molecular weight starts by looking for the highest molecular weight peak and checking to see if it is even, then all the fragments should be predominantly odd. If it is odd, then all of the fragments should be predominantly even.